Welcome to AP Podcast 17.2b. What we're going to do in this one is completely describe a galvanic cell. And so if you think about what we've been doing with our galvanic cells, and again, we're talking about something like this, what we want to do is we want to be able to describe that, and eventually we want to be able to draw a picture just kind of representing that. So that's what this podcast is about. So we start with looking at what's called line notation, and there's just a couple basic rules that we got to pay attention to. First of all, we write the solid. Okay, so in the last reaction we had copper, right? And then whatever liquid was floating around, and in the last case it was copper 2 plus, right? And then whatever this is representing either the salt bridge or the porous disk. This is separating the two beakers in our situation. And then whatever else is aqueous in the last one, it was iron 2 plus and iron 3 plus. And then the solid, and in the case of the last electrode, let me show you real quick just in case you've forgotten. The last electrode, here's that platinum right there, right? So we've got a platinum catalyst floating around. So to do that, just to represent that, all we have to do is just write PT. Okay, so that kind of represents the galvanic cell. Now, if it were a situation where both these were aqueous, then I would have another platinum cell over here, right? And I'd have two ions there. So that's how we represent that. And if you can see a nice professionally made one right here, that's how it should look. Now I got a little lazy and I didn't put the states of matter, and I definitely should have done that. So you can see right there, we write those all in there. So on to a couple other notes. When we're going to describe the galvanic cell, there's a few things we want to pay attention to. First of all, the cell always runs in the direction that is going to produce a positive cell potential. And for us, that's typically this way, from the left side to the right side. And so when we're going to draw out a cell, there's a couple things, well, there's four things we have to make sure. We have to make sure we show the cell potential. So for example, let's say 0.47 volts, right? We've got to show the direction of the flow. So there'll be some electrons and there'll be some arrows and so on. And then we've got to designate which one's the anode and which one's the cathode. Remember, reduction occurs at the cathode, right? And then we've got to list the natures of all components, okay? And that's whether they're aqueous or they're solid, if we're using a platinum electrode and so on. So let's look at a typical problem and give it a try. All right, in the last podcast I mentioned how we'd have to maybe figure out which one's going to happen. Let's go and get the reduction potentials for these two half reactions. So we've got silver being reduced to solid. So let's define that one. Silver being reduced to the solid, looks like it's right here at 0.8. Okay. Okay, so that gives me 0.80 volts. Okay. And then iron being reduced to iron 2 is 0.77. Let me write that down. 0.77. Okay, oops. Now, here's our issue. These are two reduction potentials. Obviously, if there's reduction, there has to be oxidation. So we've got to flip one of these reactions. And there's really only one combination to flip to get a positive reduction potential. And hopefully you would agree with me that we've got to flip the iron, because if we flip the 8, we get negative 0.80. We can't get it positive. So let's just write the whole cell here. All right. So we're going to flip this. Actually, it would have been better. Here, let me do this. This would be better. If I go Fe2 plus yields Fe3 plus an electron, and that gives me a negative 0.77 volts. Now I'll put my line. I'm going to write out the whole cell. So I've got Fe 2 plus silver yields silver solid plus Fe 2 plus. And I should be putting aqueous, solid, aqueous, and aqueous. Okay? And then to add these up, I get a value of 0.03 volts. Wow. I don't know about you, but I'm not going to be making a silver iron battery with these two samples right here. That's not much for voltage, 0.03 volts. Okay, so I've done one part of it. I've written out the full reaction. I've calculated the voltage. Let's see what else we have to do on here. Let's see. I've done the cell potential. That's really all I've done. I've got the rest of these to do. So for the rest of these, point 2, 3, and 4, I'm going to have to use my awesome artistic skills, which you guys are very familiar with. So here we go. I'm going to draw my one large beaker, right? And my other large beaker. And I've got some kind of porous disc here, salt bridge, right? All right. And then right here, this is, let's see, who's being reduced and who's being oxidized, okay? Well, this is being reduced, right? And this is being oxidized. Remember, this got flipped, okay? So this is occurring over here. Now look at the state of matter both these are in. They're both aqueous, right? So we're going to have ourselves a platinum cathode, PT, right? And then floating around in the solution are going to be Fe3 plus and Fe2 plus. Okay, and then over here, a voltmeter with a whopping 0.03 volts. You guys liking these drawings? Feeling pretty confident about this. All right, and then over here is a silver bar. Let's make it a little thicker. Oh yeah, this is some classic Richardson drawing right here. Okay, so there's a silver bar. And then floating around is some silver plus, right? Okay, so let's see, what have I done? Let's see, I haven't done the direction of flow. I've kind of done that one. So the flow, right, electrons are going this way. Boy, this is almost fun. Okay, so electrons are going that way. This side is the cathode, right? And this side is the anode. And I think I've got it covered. Let's see. I've got the direction of flow, I've got the anode, the cathode, and I got the nature of all components, electrons, and ions. So there you go. We've just described the whole cell. Not too bad, right? I hope you think so, because you'll get to do that in class. So, if you have any questions, like always, we'll talk about it in class. See you next time.